All right, let's just get started. Welcome to CS3510. What is this? L12A, and the topic of today is NP-complete graph problems. Before we do so, let's quickly recall what we did last time. We are talking about conditionally proving that some problems are hard to solve in the sense that the best algorithm for them is exponential time. Now, unfortunately, we can't prove with absolute unbeatable certainty that any of these problems are actually hard to solve. We just have overwhelming evidence and a 99% certainty that they are actually unsolvable. Sorry, solvable, but exponentially so. We have something that looks like this. We say P is here. We say NP is here. P is problems that are deterministically solvable. NP is problems that are deterministically verifiable. And then we create this class called NP hard, and we note where it intersects with NP to be exactly the problems we're interested in. These are the NP complete ones. These are NP hard. NP hardness isn't really a class. It's kind of like a property. Right, and we mentioned that we can do a polynomial time reduction from A to B to mean that we can create a polytime computable function f such that x is in A if and only if f of x is in B. And the reason we do so is that this polytime computable function is a bit like glue in the sense that it entangles two problems together in the sense that they enter the suicide pact. They're either both easy, they're both hard. And we prove that B is in P implies A is in P. And contrapositively, if A is not in P, i.e. A is hard, that implies B is not in P. Now, proving that A is not in P, hard. Proving that A is not in P implies B is not in P, easy. You can prove this implication much simpler than you can prove the hypothesis. We don't know any problem that's in NP but not in P. Otherwise, that would just be P equals not equal NP. But if this was true, then it's true for B as well. But we don't know how to find this yet. But that's kind of what the setup is, right? To prove a problem NP complete, you must show to prove B is NP complete, you must do two things. You must do first prove that B is an NP. You do so by giving a deterministic polynomial time verifier. The verifier takes as input a witness, if you recall, right? We'll say X, sorry. And just checks the witness. And if it can do so in polynomial time, then the problem is an NP. It's an autograder. Can you write an autograder faster than you can solve the problem? If so, the problem is an NP. Second, there's a few ways you can do this. You can say for all A and NP, there's a polynomial time reduction from A to B. This is kind of cumbersome. Two guys, Cook and Levin, did this for us already independently. So instead what we can say is choose known NP complete problem like SAT and prove that there is a reduction from SAT to B. Equivalently, 3 SAT to B. Right? You don't have to do a reduction from all of NP. Just do a problem from one you already know. Recall the way we did this was we proved SAT was NP. We assumed SAT was NP complete, and we kind of illustrated that giant circuit, which would prove it's NP complete. And then we said there's a reduction from SAT to 3 SAT, and then there's a reduction from 3 SAT as well to circuit SAT, right? So those imply that 3 SAT and circuit SAT are both NP hard because they come from SAT, right? So in some sense, they're harder than SAT. And if it's plausible to you that SAT ought to be hard, then so is 3 SAT and circuit SAT, right? Just a quick, speedy review of what we did. Yes?
Sorry, so for every A that's an element of NP, A is reducible to B. That's proving NP
hardness, yes. But note that this is difficult to do because how do you do it for all A and NP? Don't do that. I mean, like, not in the case that it's hard to do, like, a good theorist should not do this because someone already did it for us. Their names are Cook and Levin, and we have their thing. Just assume SAT is NP complete already. Therefore, everything reduces to SAT, right? By the way, Cook-Levin states what? For all A and NP, there's a polynomial time reduction from A to SAT. And then by transitivity, if you can go from A to SAT, then you can go SAT to B, then you can go A to B. So you do the reduction for free, in some sense. All you have to do is reduce from a single problem, SAT. Kind of interesting that all these problems reduce to a single problem. They are, in some sense, universal. Right. Questions so far on just a quick, speedy review? One thing that may be concerning to you is that it is perhaps objectionable that we are working in a framework of decision problems. A decision problem is one that is framed as a yes or no question. But this takes immediate opposition because it's like not every question can be phrased this way in a way that is useful. Sorting is like, what is even decision variant of sorting? It doesn't make sense. So I claim that it doesn't really matter. And that we simply assume decision problems because it makes everything much easier. You get transitivity, you can do things. You can rederive an entire theory of NP completeness using functions. It's difficult, it's really ugly, and it's very, very hard. It's just more cumbersome, and I've seen this in like papers, and they try to do this. It's not good. But I claim that there is a transformation between search and decision that preserves easiness and hardness. So we say decision SAT is easy if and only if search SAT is easy. So what do we mean by search SAT? Decision SAT is the set of strings that are encodings of C and Fs such that phi is satisfiable. In the sense that there exists a satisfying assignment. Like, you don't have to actually output the satisfying assignment, you just have to say that one exists. Recall, we actually gave an algorithm to count spanning trees using the determinant, but it didn't actually tell us what the spanning trees were. It told us how many solutions there were without telling us what any of the solutions were. So in an analogous way, you would think maybe is there a difference between determining if there is a solution versus what the actual solution is? For the decision version of SAT, we ask, is the formula satisfiable? For the search version of SAT, we seek a function that computes in poly time, that takes as input phi and outputs the literal satisfying assignment. What is the solution? Not is there a solution, but tell me what the solution is. Okay? That's the difference between a search problem and a decision problem. Decision problem says yes or no. Search problem is actually output what the answer is, not just that it exists. Right? Why is this implication easy? If search SAT is easy, why is decision SAT easy?
Find a solution, there's obviously an agreement that satisfies it.
Yeah, so let's say you find a solution. You know what the solution is. So instead of returning the actual solution, just output true. Okay, so search to decision is pretty easy. What about decision to search? I claim, and this is the kind of the core of the argument we're making here, if the decision version of SAT is easy, then the search version of SAT is easy. Analogously, if one is hard, the other is hard. So they're either both easy or they're both hard, right? How is it the case, there's two words I'm looking for as an answer. If someone can solve the decision version of SAT easy, then they can actually find the satisfying assignment easily. So if SAT is in P, search SAT, you can actually output the solution in polynomial time. I claim that can be done. Why? Yeah. But there's exponentially many of them. There's two words I'm looking for. The construction here is a bit creative. The two words are binary search. We have a polynomial time algorithm for SAT, We can binary search over a truth table using this polynomial time algorithm, and it will tell us whether or not what the actual satisfying assignment is. So for example, let's suppose we ask first, is phi in SAT? We have some algorithm and we ask it this. If it says, yes, this is satisfiable, now this algorithm outputs a Boolean for us. It does not output the actual satisfying assignment, but I claim we can actually learn the bits using this algorithm. We basically play binary search. We play hot or colder and trick it into telling us what the actual satisfying assignment is. We do so as follows. If it's satisfiable, then we continue, and we ask it about phi and x1. And we ask it about phi and not x1. Let's suppose phi is satisfiable. You run the algorithm 3 times at this point, okay? What do we know that if phi is satisfiable and phi and x1 is satisfiable? Here by and x1 we mean we add a new clause of a single variable called x1 for whatever the first variable is. If phi is satisfiable and phi and x1 is satisfiable, what do you know about the satisfying assignment?
It includes x1.
Yeah, if this is satisfiable, all clauses must be satisfied, including that one. So what that means is that if this returns true by the algorithm, then x1's satisfying assignment is 1. If it doesn't, try this one, and if this is 0, if this is 1, then you know x1 is 0. So you can set the bit here of the actual output of the satisfying assignment to be which of these recursive calls, not recursive calls, just calls, which of these returns true, right? So you binary search over this space, then you try phi and x2, phi and not x2, right? How many times, let's suppose SAT is in P, this algorithm takes O of n to the k time. You run that algorithm how many times? Let's suppose there's n variables. O of n times. Let's 2 for each variable, so that's 2n plus 1, right? This is O of what? Yeah. So that's polynomial, polynomial, polynomial. You can extract from if someone can tell you an answer, you can extract from them answers to other questions, which will tell you the actual answer you're looking for. If they tell you an answer exists, you can actually find what the answer is. This is why it's not too bad for us to consider decision problems, even though you may think they're not general. It's okay. These kind of things exist, and so it's fine. It just simplifies some of the math for us. Questions on that? Okay, I claim that there are NP-complete graph problems. Specifically, we spent a whole unit on graph problems that are easy, that require strong local properties. There are several, and in fact many NP-complete problems that are based upon graphs. Given a graph G and a number k, we ask, does G have an independent set of size k? What is an independent set? The independent set is a selection of the vertices such that set of vertices such that no two share an edge. Okay? We ask, does a graph have an independent set of a certain size? Let's say I give you this graph. Give me any independent set of that graph. Yeah.
Just the middle vertex.
Yeah, that's a independent set. And in fact, you can't add any more things to that. That is not a maximal independence, but it is certainly an independent set. It is a set of vertices that, of the set of vertices, shares no edge with anything else. So since it's size 1, that actually is true. But I claim there's a larger, give me a larger independent set. Did I add 7 vertices?
Yeah, you did.
Yeah.
So if I add these 3, can I add any more? Yeah, I cannot. This one would be touching this one would be touching this one, these two would be touching that one or that one, right? So in some sense, is this maximal though? Can you find an independent set of size 4? Not really, no. Okay, so in a wheel graph like this, you can take the round down and take divide by 2 the outside and round down. Okay, what if we had a graph which was complete? In the sense that every vertex is connected to every other vertex through a single edge. What's this largest independent set?
Any vertex.
Okay. Is there a larger one? Yeah, they're all connected. Is there a smaller one? The empty set is always a independent set. What about a bipartite graph? We know what that is, right? There was a problem on the homework, I think, about bipartite graphs.
Yes, there was.
Oh, yeah.
Nope, already did that one? Hold on. Okay, yes. You partition the set into, by the way, a graph is bipartite if and only if it does not contain an odd cycle, right? So a graph can be drawn in such a way, what is an independent set of this graph?
One side of it.
Yeah, just choose one side or the other because by definition there can't be anything connecting there. And those definitely share no edges with each other. They can only share edges with the other thing. So an easy way to find an independent set of bipartite graph, choose one side or the other. Every NP complete problem actually has easy subproblems, right? So in fact, these are kind of like easy cases where if the graph meets a certain criterion, you can just say, oh, okay, yeah, that's obviously the independent set. If it's bipartite, if it's a clique, if it's something exotic like a wheel. But in general, finding a independent set of a certain size in a graph is NP complete in the sense that you cannot always do it. It is NP complete. It's as hard as solving SAT. So that's what we're going to prove. But every hard problem has easy subproblems. Again, SAT has, as a subcase, 2SAT, right? So trivially, that's like polynomial time. Well, not trivially, it was a homework problem, but it was polynomial time. But that's a polynomial time subproblem. But in general, the bigger problem, hard to do, thought to be exponential. Now, if I asked you to solve this, what is an algorithm you could conceive of? Yeah.
Consider every possible set of vertices of which k size.
Yeah, how many of those are there?
2 to the k.
Yes, it's going to be cardinality V. There's two answers here that both give the same runtime. V choose k is approximately of size n to the k. Let's just say this is V. Let's just say the cardinality V is n. This is approximately n to the k. Okay? Now that looks like a polynomial. Problem is k is part of the input. So the exponent of the runtime is a function of the input. So this is actually like log of the size of the input, which is going to be kind of like log n. No, maybe more. This is not good. It's bad. So basically the only thing you can do is brute force search. Suppose I asked you for a search problem version of this. I asked you for the maximal independent set, right? You're not given k to determine. This k here is just to decisionify it, to ask is there a set of a certain size. But I ask you for the maximal independent set. What would you do? Yeah, how long would that take?
Two to the n.
Yes, why?
Because that's how many possible subsets of vertices there are.
Exactly. There's 2 to the n possible subsets. Check them all. Yeah. Anyway, so this is a hard problem. We did many easy problems because graphs have lots of local properties. But in some sense, an independent set is not local. A path in a graph is nice because inside the path contains smaller paths, right? And it is true that inside an independent set is a smaller independent set. And you would think, oh, maybe there's a greedy way to do this. But it's not true that you will always achieve something maximal. That can be not a bad approximation strategy, but it doesn't solve the problem perfectly. The way to, before we get into the meat and potatoes of this specific reduction, let's talk at a high level how the correspondence works, right? We are looking, and we'll do from 3SAT, we are looking specifically for a reduction from 3SAT to independent set. We want to be able to translate the problem from 3SAT to independent set. Now we're taking a formula and we're outputting a pair of a graph number pair. And we seek to be able to perform this transformation in polynomial time. That means the translation must occur faster than the solving can occur, right? The reduction does not have access to the actual solution. It somehow has to preserve this correctness. One thing to think about is how small local decisions now a reduction need not preserve anything except the correctness. But while a reduction translates problems to problems, a good reduction can do much more. A good reduction should also not only translate problems to problems, but solutions to solutions. In the sense that if you actually did know the satisfying assignment, you could use the reduction to actually find out the independent set. So the actual satisfying assignment corresponds to the actual independent set. The solution can be translated to the solution. Now that's not required, but a good reduction should do that. By the way, in NP completeness, there's at least 3 notions of a reduction. There's something called a Karp reduction, a Cook reduction, a Levin reduction, a parsimonious reduction. There was a book. The appendix had 13 different definitions of reduction. It's too many. There's all these kinds of properties you could require and ask a reduction to do for you. We do the bare minimum. We ask it to be correct. But a good reduction can do more. It can translate solutions to solutions. It can also translate the number of solutions to the number of solutions, and so on, right? And the reason I mention that is that decisions to find one solution in what you're mapping from can translate to decisions to finding solutions in what you're mapping to. For example, if you are working in SAT, let's say you have A or X or B and C or not X or D, right? As you make certain decisions, you are prevented from choosing other options, right? Decisions implicate other decisions. For example, let's suppose you chose X to be true. Then this clause is satisfied, but then you know that this literal is not. So if X is true and it ought to be satisfiable, what do you know must be true?
C or D.
Yeah, one of C or D must be true, in the sense that choosing X forces you to choose C or D. Similarly, not choosing X forces you to choose A or B, right? Whatever those are as literals, maybe they're negated or something, right? But decisions can force other decisions. And not only can decisions force other decisions, but decisions can prevent other decisions, in the sense that you can now not choose to have C and D be false. You cannot have a satisfying assignment with X being true and C and D both being false. So some local decisions can implicate other local decisions, right? The reason I'm mentioning it like this is because when we do the reduction, that's kind of what we're going to do. And when we consider how we choose an independent set, right? We have a very similar property in the sense that, let's suppose you're building an independent set vertex by vertex. The same way you may be choosing variables to be true and false, variable by variable. As you consider a node, it prevents you from considering other nodes, right? When does that happen? Yeah, if you choose a vertex, you are prevented from choosing its neighbors. So what if we did this? If you choose X in your independent set, actually this is not exactly what it should be, but if you choose a vertex in your independent set, let's do this for now, right? You are prevented from choosing these 3 as your independent set, right? So certain decisions can implicate other decisions. And choosing vertices is basically analogous to choosing variables, right? The reason I mention this is because this is going to be not necessarily a difficult reduction, but it's the first one that's kind of a different kind. What are the reductions we've done so far? We went from SAT to 3-SAT, and then we went from 3-SAT to circuit SAT, right? Those are all formulas. Those are all logic problems. That's fine. You go logic to logic. That's okay. This is a genesis problem in some sense because it's a graph problem. So we're going from a Boolean formula to a graph. Those are very different data types. So we need to explain this reduction in depth quite a bit, right? Before we do that, though, what do we need to talk about? To prove an independent set is NP complete, what do we need to do first? Yeah, first we need to prove that independent set is an element of NP. This is always easy. We seek a verifier on input a graph and a number. What should our witness be? We are proving not SAT is an NP. We've already done that, but independent set is an NP. It's at least verifiable.
Bunch of vertices.
Yes. So let's call them V1 to Vk, which are not the set of vertices of G, but just some subset of vertices, right? And then what should our verifier do?
Check if any of them are neighbors to each other.
Yeah. We'll actually do one thing before that. Check that the witness is exactly K vertices. You need to do a little bit of syntactic sugar to make sure that you don't accidentally get a malformed input or something, right? Then you need to check, how would I, describe to me in more detail how I would do, how would I check that for a set of vertices there is no edge between them? The way I'll implement that is like this. For Vi in the witness, for Vj in the witness, ensure that Vi, Vj is not an element of E of G. Okay. The reason I'm being a little bit expository upon that is sometimes it's convenient to determine what the runtime is. What's the runtime of this? Yeah, this set of vertices is at most n, where the graph is completely independent, and double for loop of n squared, that's a polynomial. Okay, fine. Yes?
How do we know that it's constant time to check that VI/VJ is not an E?
Don't care enough. But like, suppose it was an adjacency matrix. I'm going to switch. Do you believe you can translate between adjacency matrix and adjacency list in polynomial time?
Yeah.
Okay, now adjacency matrix lookup is constant, so let's just assume the input is adjacency matrix because it'll make things easier. Boom. Now if it was adjacency list, I would have to loop over.
You could loop over the edge and just make sure. Just loop over everything
Yes.
to make sure.
But I'm lazy, so I don't want to count that as part of the runtime because I already wrote it down, so I'm going to retroactively say we're working in adjacency matrix form. Complexity is fun for reasons like this because a lot of little data structure problems are really like not my problem. You know, it's like, as an algorithm designer, it's really kind of your problem. Not an algorithm designer, excuse me, an engineer, right? All right, so we've proven that independent set is in NP, and what that really means is we've shown it's somewhere in here. It's at least not super hard that it's unverifiable, because we can at least confirm to if someone tells us I have an independent set of size k, you can at least efficiently believe that they're true, right? Now we seek to prove that it's the hardest problems in NP, and that it's somewhere over here. That'll make it harder than all of NP yet in NP, so therefore it is NP complete. What we seek is a polytime computable function such that this formula phi for any phi is in SAT if and only if some graph G and some K is in independent set. And specifically, again, this reduction is going to go from all formulas to perhaps some graphs. But all we care about is that the reduction ought to be correct, right? So we're going to basically use this property here to get the specific graph that we want. Also, I should be writing 3SAT here. We usually reduce from 3SAT instead of SAT, only because it makes they're equivalent, right? But it makes all the reductions simpler, as you'll see. Not in a like big O sense, but like, usually not in a big O sense, but in a, like they're easier to write, easier to explain kind of way. So, let's suppose we have a CNF of the following. We have not x or y or z, and x or negation of y or z, and x or y or z, and not x or not y. By the way, is the definition of 3SAT that it must have exactly 3 literals per clause, or at most 3 literals per clause? Yeah, it depends. At most, here, because I wrote the one with 2, but it depends which book you ask. 14 out of 15 books will say, at most, one book says exact. It doesn't matter because there's a reduction both ways. You can reduce from at most to exactly, and then from exactly to at most, almost trivially. You can go from at most to exact by padding, and then exact is already at most. So like the reduction, it doesn't matter. You can assume whichever one you're working in, whatever will make the proof the most convenient. Okay? Now we want to ensure an independent exists in a graph of a certain size. So what we're going to do is actually construct a triangle for each clause of the following form. And by the way, the reduction, as I'm doing it, has two parts. First, you have to describe what the reduction is, in the sense that a function exists, a polynomial time algorithm exists that runs in polynomial time, takes as input a formula, and will output a specific graph. So then you have to argue the if and only if part. So what I'm saying out loud is all that should be written down in the proof, and it is in the notes, but I'm not going to write down the paragraph to describe it. I'm just going to say it out loud. What we do is we create a triangle per clause. So, and we label these as follows. Oh, this should be that. And why? Oops. Okay. Okay. So if you choose a literal to be on, a variable to be on, it prevents you from choosing that literal to be off. Analogously, in our independent set, what should we wire up? Yes, but in what way? The negation of it. If you choose X, you should be prevented from choosing not X. So let's say you choose this as your independent set. You should not be allowed to choose anything that corresponds to it. So anything that's a negation of X is not choosable. Similarly for the Y's. So for each Y, you connect it, wait, is that it? Oh, one more. For each Y, you connect it to each negation of Y. For each X, you connect it to each negation of X. Also, double check me if I'm missing anything. X goes to XX, X goes to XX. Yeah, that's fine, right? Okay. And then Z's are going to connect to the negations of those. Okay. This is the following graph. Am I missing any edges? Anything look off? Seems right. Okay. Now, what is a maximal independent set in this graph? Without looking too closely at it, suppose we have such a chaining together of triangles. What could a maximum independent set in this graph be? Well, an independent, notice that any independent set, what are the triangles enforced with the independent set part?
You can't have, it has to be part of another.
Yeah, you cannot, well, that's that too, but let's forget the connections between triangles. Just look at the triangles. If you have only the triangles, what's the largest independent set you can have? No. Yeah, it's the number of triangles. You cannot have two vertices in each triangle. So if you have some number of triangles just laying next to each other, the largest independent set you can have is the number of triangles, because you choose one from each triangle. You can't choose two from a triangle, so it can't be larger than the number of triangles, right? Otherwise, by pigeonhole, there would be two in a triangle. So you can't have this. So the maximum independent set is already the number of triangles. What is that how many triangles are there from the CNF? What does that correspond to? Yes. So the reduction will take the formula phi, and I'll put a graph G, comma, K, such that G is as above, everything I wrote down, and just pretend that I wrote all that down. And we set K to equal the number of clauses. Before we do the proof, let's convince ourselves that every satisfying assignment corresponds at least to some independent set, right? What is a satisfying assignment to this formula? I'm asking you to find an assignment to x, y, and z that satisfy this formula. Yeah.
X is false, Y and Z are true.
Okay. Does that work? Let's see. Y is true. Z is true. Y and Z are true. X is false is true. Okay, that's satisfying assignment. What corresponds to, what is the solution that is mapped to by the solution we just inspect? X is 0, so we would choose this one. Y is 0, but Z is 1, so we would choose this one. X is 0, but Y is 1, so we choose this one. Now we set X to be 0, so not X is 1, so we choose this one. Okay. Two questions. First off, is that an independent set? Are any of the vertices I've selected adjacent to each other? Okay, good. Is it of size 4? Which is exactly the number of clauses. So that's going to, I'm doing this before we do the proof so we can kind of like see how it's going to line up, right? Questions on this so far? If you chose a different independence, if you chose a different satisfying assignment, you get a different independent set. Another thing I want to point out is that this specific satisfying assignment does not uniquely correspond to an independent set. Why? Sorry?
Does it depend on the order of clauses?
Not necessarily. Clauses are commutative, yes.
In the third triangle, if you circle Y instead of circling Z, you also get another valid
Yeah.
set that corresponds to the same assignment.
Exactly. It's not necessarily true that the satisfying assignment, the independent set must be unique from the satisfying assignment, just that there is one, right? So in fact, and you can turn a clause on in multiple ways. It's not the case that each clause must be uniquely satisfied, but just satisfied. So in fact, with Y and Z both being 1, this clause is satisfied with 2 lights on. It's over-satisfied in some sense. So I could choose this one or this one in the independent set, but not both, right? So in that sense, it's not unique. Let's prove the reduction. Let phi be an element of SAT. Then it has some satisfying assignment. To its K clauses. Consider G comma K the output of the reduction. Well, first consider G. Consider G, right? We've actually kind of said the reduction out loud already. Let's just formalize it. What is the largest independent set in G? By this triangle construction, G has an independent set, if any, of size less than or equal to K. It can't have more than that, otherwise any set of size K plus 1 would cross in any triangle, therefore they must be less than them, right? Now if G is a satisfying assignment, for each clause of the satisfying assignment, choose a vertex of the corresponding triangle and add it to a set. Note this is an independent set of size K. So G comma K is an independent set. We've proven one direction of the implication. Sometimes you're stating something obvious, sometimes it takes a little more contrived explanation. Now we want to prove this if and only if. And again, there's 2 ways to prove an if and only if. To be pedantic, if you want to show P if and only if Q, you could do 2 things. P implies Q, and Q implies P. Or P implies Q, and not P implies not Q, right? Whichever one you choose is just a simple, it's not very important. It's just a proof strategy. So we always need to do P implies Q, phi is in SAT, G comma K is an independent set. Now which one would we rather prove? Q implies P or not P implies not Q? What do we think? Just looking for a poll for the audience. What do we think ought to be easier?
Probably not P implies not Q, so we don't have to make another reduction.
Yeah, both are equivalent, right? In fact, this is the contraposition of this one, if you agree. I'm asking, we're doing this step. Sorry. We're doing either this step or this step, right? But the one is the contraposition of the other, so they're both logically equivalent. But in terms of efficiency and elegance in the proof, which one ought to be better? The not P implies not Q? So let's just kind of explain both. Let's suppose we tried not P implies not Q. And this is not an important detail, and it's totally okay to choose one or the other. But I'm just going to explain a heuristic about why I would choose one over the other. If you try not P implies not Q, you would say, okay, let phi be unsatisfiable. Then no satisfying assignment exists for it. How do you argue that every independent set that exists, none of them have size exceeding K? I don't know. That's kind of like, it's probably possible. But the other one sounds easier because you get to assume the following. You get to assume that an independent set exists, and then you can argue about the independent set. Rather about arguing about a lack of a satisfying assignment, it's easier to argue about the existence of an independent set. Now there are certain problems you want this one instead of this one. I'm pretty sure graph problems you want this one. So this is not important, it's just a heuristic. Suppose G comma K and this is not just a general G comma K, but specifically a G comma K that is the output of the reduction. Not a general one, but a specific one. Suppose G comma K is an independent set. Then there is I, which is a subset of V of G, with the cardinality of I being K, and no edge shared of the vertices of I. It's independent, right? Since G has these K triangles, and yes, we can call this line a triangle, it's fine. Exactly one vertex of I is in each triangle. This corresponds to a satisfying assignment of phi. So phi is satisfiable. QED. We've proven the if and only if, so we know that there is a reduction from SAT independent set. We also proved independent set was an NP. There's actually one thing we forgot, now that I think about it. There's one thing we forgot to do in the proof. Not in the proof necessarily, but in the argument that independent set is NP complete. There's one thing we forgot to mention. Anyone know? We need to argue that the reduction, and the reduction is a computer, it's a program that takes as input a formula in whatever syntax and outputs a graph in whatever syntax. Adjacency matrix, list, it doesn't matter. But we need to argue that the reduction takes polynomial time. We don't need to give too precise in the big O, but we need to argue that the reduction can write down this graph in polynomial time. Can it? There are n variables in our CNF. There are like 3n vertices at most here, and then there are like 3n choose 2 at most edges to apply. That's all polynomial. N choose 2 is like O of n squared, so that's like This is approximately O of n squared. The reduction takes approximately O of n squared. So we would need like a brief sentence on why this obviously takes polynomial time. Yes?
For those two, that should be the, say, 3 sat, not
Oh.
sat.
Thank you. That is a bad habit of mine. Suppose we did this reduction not from 3 sat but from sat. What would change in our triangles?
There would be n gons.
Yeah, well, no, actually, they wouldn't be n-gons. Generalizing correctly, but in the wrong way.
There would be something gons.
They wouldn't be line graphs, I'll tell you that.
What do you mean by line graphs?
We want the property, not that just that these are triangles, but they're really not triangles in a geometric
But they
sense.
would be clicks.
Yes, they would be connected, fully connected graphs in the sense that this would not just connect to these two, but if there was 10 things here, it would connect to all 10 of those, right? Observe the economy and proof how we get to say triangles instead of, what if these are cliques of different size? And then like, you know, how do you wire that up to that? And then to, it's like, it's just uglier, right? It could be done, but it's, don't do it. So like 3 sat makes things simple, right? That's another reason we think about 3 sat more than we think about sat. Okay, we've proven the reduction. You should be fully convinced that you cannot solve independent set in polynomial time. It's hard to solve. Questions on that? Okay, let's do some other graph problems. Speaking of cliques, let's just do cliques. I claim finding a clique in polynomial time is impossible. Clique is the problem of given G comma K, does G have a clique of size K? Okay? What is a clique? A clique is one of the following. It's that, it's that, it's that. Oh. It is, in some sense, the most dense graph. Okay, I think that's right. This is a clique of size 6, 5, 4, 3, 2, 1, okay? We all know what a clique is. Easier to just point at and say that's a clique than it is to say, you know, there's a set of vertices. A clique is not just a graph that looks like this, but a graph has a clique if it's a subgraph of it, right? So some portion of the graph appears to be a clique. The same way a portion of a graph could be independent, but the whole graph, of course, could be connected to each other. A subgraph is said to be a clique if a graph is said to have a clique of size k if a selection of the vertices are fully connected to each other. It's called a clique in the sense of a friend group. Everyone knows each other, right? If the edges represents a relationship, A knows B, then the clique is the largest group of friends that all know each other fully, right? Clique, I claim, NP complete. Why? Well, let's just do it, actually. First, we need to show clique is an NP. Why is it an NP?
You just give them the vertices complete, you can check that they're all connected to each other.
Yeah. So the witness is, I'm going to do a magic trick. Watch this, hold on.
What?
This is the verifier we gave that independent set was an NP. What are we going to do here? We're going to erase that, call that clique. The verifier takes as input a graph and a integer, a natural number, and asks, does the graph contain a clique of that size? The witness is going to be a selection of vertices. It checks that the witness is exactly size k, and for each pair of things in the witness, ensure not that vi vj is not in E, but is in E. Okay, done. Wait. Oh, then I'll erase that. That's the verifier that ensures that a clique is an NP. You can verify a clique exists in polynomial time. Yes?
Don't we also need to make sure that VI and VJ aren't the same node?
Yes. Now, okay, fine. One of those little syntactic sugar things. Yeah.
Just a thought, I'm getting ahead, but could we take that graph from 3SAT and then take its like edge complement? Can we add everything that's not there?
We don't even need to do that. You see the solution, but I'll tell you the simpler way, which is exactly what yours is the deeper intuition part. A reduction is transitive. You go like this.
Oh, so we could just reduce from the other thing.
Exactly. If you have, if someone claims they can solve this problem in general, they can solve your problem in specific. So if someone claims they can solve independent set in general, then they can solve it in the special case of graphs that are these combinations of triangles. And if they can do that, then they can solve 3SAT. Note that the reduction is not surjective in the sense that it outputs every possible graph, right? There are so many graphs that are not just combinations of triangles like this. But inside these circles are the graphs that are like only triangles, satisfiable and unsatisfiable, right? But they claim they can solve it in general, right? Similarly, we're just going to go from independent set to clique. So if someone claims they can solve clique in general, they can solve independent set in general. If they can solve clique in general, they can solve independent set in specific. Wait, if they can solve clique in general, they can solve independent set in general, which can solve 3SAT in general. So that's kind of what we're going to do. We don't need to do a complex reduction from SAT to clique. You want to choose a problem to reduce from that is closely associated to one that you already know. So rather than reducing a logic problem to a graph problem, now that we have at least one graph problem to be NP complete, you can choose to reduce from that for free. Question?
You missed a line on the right side there. The bottom one of the good set.
Where?
I asked a clique.
What?
The
Oh, thank you. Okay, yeah. We get it. Thank you. Okay. We proved clique is an NP. Let's give the reduction. We will give the reduction now from independent set to clique. Efficiently so. So we seek a G comma K in independent set to map to a G prime, let's say, K prime in clique. Now, we don't need to map to the same graph. We don't need to map to anything related. We just need a problem to map to a problem with this correctness property that good goes to good and bad goes to bad. It need not be the same problem at all. So give me a graph that has an independent set of size K if and only if a different graph has a clique of a perhaps different size K prime. What is the connection mathematically between a clique and an independent set? What does that mean?
And like, for a clique, every edge has to be there, and for an independent set, every edge has to not be there.
Okay, so if G has a clique, an independent set of size K, what graph has a clique of what size?
I don't know what to call it. Could you call it G complement?
Yes.
It has all the edges.
G complement, which is equal to V comma E complement, has a clique of what size? Okay. So I'm just going to erase that. Okay. The reduction in polynomial time takes as input a graph and a number, leaves the number alone, and just reverses the edges. However that's done, it doesn't matter, it's polynomial time. Just look at each edge, change the bit in the adjacency matrix. If you're doing a list, it's probably just still E to take a list and flip it, right? V squared, in the case it's dense, but we could say it's E. Yeah, fine, V squared, if it's at most, yeah. Because then that gets to say the reduction takes n squared time, okay, fine. Okay, now why does it work? consider a reduction that goes from G comma K to G complement comma K. If G comma K is in independent set, there exists I, which is a subset of V with I of size K and independent, right? Let's see. Consider I a subset of V, but of G complement. Since in G, no vertices of I share an edge, in G complement, all vertices in I share an edge. Thus, I is an independent set of size, excuse me, nope. I is a clique of size K in G complement. So G complement, comma K is an element of clique. Done. Before I do the second direction of the if and only if, why don't I just give you a picture of a graph complement so we don't have to play pretend here, okay? Let's do so this is an interesting graph. What is that, a prism? Everywhere there isn't an edge, let's add an edge, and everywhere there is an edge, we will make sure there isn't. Oops, nope. So we're going to do this. Okay, what vertices will this one be connected to?
The two up there, like,
Yeah, it's connected to the other one, so by symmetry, we can just do the same for this. What kind of graph is that? It's a polygon. Yeah, that's a. It's interesting that the graph complement. This is, I don't know if how this generalizes or whatever, but the complement of a hexagon graph is exactly this triangular prism. Kind of a cute little thing. You could redraw this graph like this, right? So, or same thing, doesn't really matter, right? Kind of a cute thing. Graph complements have some interesting properties, so I'm trying to illustrate. Let's finish the second direction of the if and only if. Which one ought we to do? Should we do not P implies not Q or Q implies P? Yeah, Q implies P is going to be easy because we can argue about the existence of an independent set. If G complement comma K is in clique, there exists I, which is a subset of V of G complement, which is a clique of size K. Note, I, a subset of V of G, shares no edges, since in G complement, they share all edges. Thus, I is an independent set of size K in G. So G comma K is in independent set. Done. The reduction took polynomial time. We have a polynomial time verifier. We did our if and only if. Clique is NP complete. Questions on this proof? Okay, let's quickly do one more. Let's see. A vertex cover of a graph is a selection, it's a totally orthogonal problem to asking for a independent set or a clique. Independent set and clique are in some sense, not in the decision variant, in the search variant are, in the search variant, these are, we are looking for a maximal set, a subset, right? In the sense that we want the largest clique or the largest independent set. The problem of vertex cover asks for, given a graph, in a search sense, what's its smallest vertex cover? And a vertex cover is a selection of the, let's say G comma K. So it's a G has a vertex cover of size K. A vertex cover of a graph is a selection of vertices that cover every edge. Right? So if I asked you, for example, for this one, we have a clique. What is a vertex cover of the clique? Select for me a set of vertices, not edges, but vertices, such that every edge is touching one of the vertices you select. Yes?
Any selection of 3.
Okay. Every edge is touching one of those 3 vertices. Is there a smaller vertex set? Vertex cover? Yeah, because if you forgot that one, you'd be missing that one. And by symmetry arguments, all subsets of size 2 are identical. What if we did something like this? What is a vertex cover of this set? The middle one? Yeah, that covers this edge, this edge, this edge, and this edge. We need something to cover this edge, so we're going to choose this one. Can it be done any smaller? Is there a vertex cover of size smaller than this? Yeah, there isn't. So, fine. But for any graph, what is any vertex cover? What is always a vertex cover?
The whole graph.
Yeah, just choose all the vertices. That's always going to cover the graph. Analogously, every graph has a clique or an independent set of size 0. So every graph has a trivially smallest independent set or clique. Here, every graph has trivially a maximal or largest vertex cover, right? I claim vertex cover is NP complete, right? First off, why is vertex cover in NP? Let's just write it down. V on input, let's say G comma K. Our witness is going to be of the form, let's say V1 to Vk. It's going to be vertices. What are we going to check?
Every edge, make sure that at least one of the endpoints are in the witness.
Yeah. There's some other syntactic stuff there. Check. W is K vertices, etc. Whatever. Right? All that other stuff. How long does this take?
E.
N squared-ish, if we say E, right? Fine. What is the reduction? First off, do we reduce from SAT? No. 3-SAT? No. We already have graph problems. It's not, so clique in some sense is just the same thing as independent set. So that reduction was trivial. This is a little non-trivial. What is a reduction from, let's do independent set, to clique? No, sorry, vertex cover. If some graph has an independent set of size k, when does a different graph, perhaps, have a vertex cover of a different size? This is tough. Think about these graphs that we've done so far. They have independent sets of certain sizes, right? What does an analogously, how does that correspond to a clique or independent set.
If you have an independent set of size n, then the same graph, if you just choose the complement of that independent set, that'll cover all the edges.
Exactly. Why?
Because there's no edges between the vertices in the independent set, so all of them must be either within the complement of the independent set or between the complement and the independent set.
Exactly. So we'll formalize that in the reduction. This is just going to be the same graph, and then we set this to be what? The size of the independent set.
V minus k.
Yes. The size of the vertex cover is just going to be v minus k. If a graph has an independent set of size k, that same graph has a vertex cover of size v minus k. Let's quickly prove it. Kind of interesting because this is not immediately like a clique or independent set problem, but it is, in some sense, it is, right? Previously, we went from clique to independent set by changing the problem. We're going to go from independent set to vertex cover, not by changing the problem, but by changing the solution. So we don't know what the solution is, but we know what size it's got to have. So if it exists, this other solution exists. We don't even know if the solution exists, but if it does, so does this one. It's power of reductions, right? Let g comma k be an element of independent set. So I is a subset of v of size k and is independent. So no edge of E is shares both ends in I. So every edge shares at least one end. Oops. In I complement. So this is a vertex cover of size cardinality of I complement, which is v minus k. So g comma v minus k is in vertex cover. Done. Right? If a set is independent if no edge has both ends in the set. So if no edge has both ends in the set, every edge must have at least one end in the complement of that set. Done. If an edge was in, let's say, this independent set, then in its complement, the vertex cover would be missing that one edge. It would not be able to cover that one edge, right? That's how the double negations work. Let's do the other way. Let g comma k be an element of vertex cover. Nope. G comma v minus k. So so G has an a vertex cover of size cardinality v minus k. So each edge has at least one end in this set I. Then no edge has any end in I complement, which is size cardinality of v minus cardinality of v minus k, which is just what?
K.
Yes. So G has an independent set called I complement of size k. So G comma k is an independent set. Done. QED. All right. Any questions? I'll take some more time. We went from all A and NP, just to give you a quick highlight where we are right now in the world. We went from all A and NP. We went from A to SAT. We didn't really do this, but it's done by the Cook-Levin, right? Then we went from SAT to 3-SAT. And then we also went from 3-SAT to circuit SAT, right? Then today we went from 3-SAT first to independent set, and then we can go from independent set to two problems. We can go to vertex cover and clique. But notice how the hardness of, let's say, vertex cover inherits itself from the hardness of independent set, which inherits itself from the hardness of 3-SAT, which inherits itself from the hardness of SAT, right? So we don't do the actual reductions all the way back down to genesis. We just kind of keep it there. And this tree exists. It has something like 20,000 leaves on it, each of them an NP-complete problem. And we'll fill in the rest of the tree, a few more nodes on the tree later today. But note that's kind of like how we're building it out. Now, if you have another graph problem you want to prove NP-complete, try to attach it to either independent set, vertex cover, or clique. Right? Any questions? Okay.